Welcome to this video. So what we're going to focus on today is we're going to focus on instrumentation, and we're specifically going to look at mass spectrometry and AAS. Now AAS stands for atomic absorption spectroscopy, and we want to understand the fundamental processes that occur in a mass spectrometer and its use in determining the relative atomic mass of a substance. So in our previous atom videos, we spoke about light being emitted, and we spoke about emission spectra. But what we're going to talk about in this slide is we're going to talk about atomic absorption spectroscopy, because atoms can also absorb light. So in atomic absorption spectroscopy, white light is passed through a gas sample, and the light that is emitted then is passed through a prism, and that causes a spectrum to be produced. So light emerges with certain wavelengths missing, and this forms your atomic absorption spectrum. The certain wavelengths that are missing are represented by dark lines, and this is caused by the element in your gas sample absorbing light. Now, if we were to compare the emission spectrum and the absorption spectrum, if we were to put one on top of the other, you should get a complete rainbow, because the wavelengths that are absorbed by the spectrum should correspond exactly to the wavelengths that are detected in the emission spectrum. So the black lines that are in your absorption spectrum should match up with the coloured lines in your emission spectrum. The explanation for this is because atoms in the ground state absorb the same radiation that they emit in the excited state. So as we can see by the last point, energy absorbed is equal to energy emitted. In short, we can say an emission spectrum consists of coloured lines against a dark background, and an absorption spectrum consists of dark lines against a coloured background. So here's a diagram to help explain this. We have our white light source, and it passes through a gas sample of an element, and the light is then passed through a prism, and we produce a nice spectrum here. So this spectrum will look like this here. It's an atomic absorption spectrum. And as you can see, the atomic absorption spectrum has a rainbow with black lines on it. And if you compare this to the emission spectrum, you can see that the colours in the emission spectrum match up with the black lines in the atomic absorption spectrum. So if we're to label this, we've got 1 and 1, 2 and 2, 3 and 3. And those numbers correspond in the emission spectrum and the absorption. So the first colour in your emission spectrum here matches with the colour that's missing from the absorption spectrum. The number 2, the green colour, matches with number 2 in your atomic absorption spectrum, and 3 matches with the red colour in your atomic absorption spectrum. It's also important to know the uses of atomic absorption spectrometry, and atomic absorption spectrometry is useful for detecting the presence of elements in materials dissolved in water. It's also useful for measuring the concentration of elements. So the principle behind the use of atomic absorption spectrometry is based on 2 facts. And the facts are that atoms in the ground state absorb a particular wavelength of light that is characteristic to that element. So only that element will absorb that particular wavelength of light. The second fact is that the amount of light absorbed is directly proportional to the concentration of the element. Scientists don't tend to use white light in atomic absorption spectroscopy. What they tend to use is they use lamps that emit the line spectrum of a particular element. So for example, a sodium lamp would be used to measure the amount of sodium present in a particular gas sample. The reason for doing this is using the same light source as the element being tested. It produces the exact same wavelength as those that will be absorbed by the sample. So the intensity of the light being detected is measured before and after the gas sample is introduced to the system. And then from this, it's possible to measure the concentration of your element, because we know that the amount of light absorbed is directly proportional to the concentration of the element absorbing it. So now let's look at mass spectrometry, and we're specifically going to look at the mass spectrometer. The mass spectrometer consists of 5 main parts, and they have the following processes: vaporization, ionization, acceleration, separation of magnetic fields, and detection. And we're going to look at each of these individually now. So for vaporization, a small amount of liquid is injected into the mass spectrometer at something called the sample inlet. And due to the vacuum present, the liquid is vaporized into a gas. Step 2 is ionization, and we've met ions already in this section. And in ionization, atoms and molecules are turned into ions. And this is done by a heated filament firing electrons at the atoms, causing them to lose electrons and produce positive ions. So as we can see here, we've got our gas atom. It's bombarded with electrons, and that causes it to form a positive ion and lose an electron. Stage 3 is acceleration, and here the ions from stage 2 are passed between a series of negatively charged plates to accelerate the positive ions. This is why a vacuum is needed, so that the ions won't collide with air particles, and that could cause them to slow down. So that's why the vacuum is needed. Step 4 is separation in a magnetic field, and here a strong magnetic field is applied to separate the ions by their mass. So the lighter ones are pushed further off course than the heavier ones. This simply means that the lighter ions are able to be moved around more easily. Step 5, the last step, is detection. And here they use a detector to pick up the ions, and a detector is just a sensitive instrument that responds to the ions as they hit off it. Changing the strength of the magnetic field brings different ions into focus on the spectrometer. So changing the magnetic field will cause different ions to hit off the detector at different times. And the results are then sent from the detector to a computer, and we form a mass spectrum. This here is just an example of what a mass spectrum will look like. And these peaks basically, as you can see, they've numbers written on top of them, and this number represents the mass. So basically, each of these peaks represents different ions that have been formed during their journey through the mass spectrum. There's many uses of the mass spectrometer. It can be used to identify the presence of isotopes, to measure the relative abundance or how much of a certain isotope are present. The mass spectrometer is very useful in measuring the relative atomic mass and relative molecular mass of substances, and this is done in further detail in the periodic table videos. And it's also used to identify unknown compounds such as banned substances in athletes, because their blood sample can be injected into the mass spectrometer, and that will then vaporize, and scientists know the components of blood, so any components that aren't in the blood may be actually unknown substances or banned substances to help improve the performance of an athlete. That's it for this video. Make sure to read the learning intention to make sure you understand everything from this video.